Bear in your mind if you have a rigid body which undergoes the rectilinear and curvilinear translation, then we can simplify it to be particle. You should know that a particle can only have two motions here. If the rigid body undergoes fixed axis rotation, like this case, as well as the general plane motion here, in this case, we can no longer simplify the rigid body into a particle. If you observe the relative motion between B and A here, as well as when the rigid body is performing the general plane motion, you will see that the RB with respect to A is different for these two cases. Therefore, when you differentiate it, the velocity B with respect to A and also the relative acceleration will no longer equal to 0. This means that the velocity and acceleration at point B and point A here will be different. Therefore, when rigid body is performing the fixed axis rotation or doing the general plane motion, we cannot simplify it to be a particle. Let's continue with the rigid body here with rotation about a fixed axis. If you see in front of the rigid body in the z-axis here, then you will see the rigid body is rotating in xy plane. So this is your front view and 3D view. In the front view, you see the point in the rigid body rotate with angle theta. The theta symbol here means the angular position or the angular displacement. Differentiate theta with respect to time, you obtain the omega, which is the angular velocity. And then you differentiate the angular velocity with respect to time, you obtain the alpha, which is the angular acceleration. So these are the formula and symbol used when we perform the scalar analysis for the angular motion. Let's convert this to the vector format. If the theta, angular velocity and angular acceleration are rotated in the same direction here, which is rotating counterclockwise in the xy plane, where you have your x and y here, and the rigid body is rotating in the counterclockwise in z-axis. Therefore, by using the right hand rule, you obtain the angular motion here to be in positive k direction. Angular velocity will be always in the same direction with the angular motion for the theta here. If you have the angular velocity equal to 0, it means this thing does not rotate. In this case, you will obtain the angular acceleration to be 0 as well. If you have the angular velocity equal to constant, so the speed of rotation will be constant, then you will have angular acceleration equal to 0 as well. If the angular velocity is not constant and is increased over time, then in this case, the angular acceleration will be acting in the same direction with omega, which has the positive angular acceleration. On the other hand, if the angular velocity is decreasing over the time, then in this case, your angular acceleration will be opposite direction to the omega. In this case, the omega is still rotated in the counterclockwise. However, the angular acceleration is acting at different direction, which is in negative k direction. This negative direction can be obtained by using the right hand rule, or you can observe the clockwise direction in the z-axis. If you have different direction between the alpha and omega, then the omega will reduce over time, because this alpha is called the deceleration. When we study the rotation of the rigid body about a fixed axis here, this fixed axis is located at the center of mass for the rigid body. Let the center point here to be the O prime, and we choose an arbitrary point here and label it with point P. By using the relative motion analysis, you should be able to obtain these two equations for the velocity and acceleration. For example, to find the velocity at P with respect to the origin at inertial frame here is equal to the velocity at O prime, which is the center of mass here, with respect to O, plus the velocity at P with respect to O prime. So after you differentiate this equation with respect to time, you should obtain the acceleration. There is a typo here. This should read A. In this case, the rigid body is rotating about the fixed axis here, which is the center of mass. When you observe the motion for the O prime with respect to O here, then you obtain the displacement O prime with respect to O here equal to 0, as the center of mass here doesn't move during the rotation. Since this term is 0, if you differentiate it with respect to time to obtain the corresponding velocity and differentiate it again with respect to time to obtain the acceleration, so you will find these two terms equal to 0 as well. Therefore, the velocity and acceleration at the arbitrary point P with respect to the O will be equal to the velocity and acceleration of the point P measured with respect to O prime here. Therefore, we can find the absolute velocity at point P with respect to O prime here. When you observe the motion at point P with respect to O prime, you see the point P is just undergoes the curvilinear circular motion. In this case, you can find the velocity and acceleration component by using the normal tangential coordinate. Tangent coordinate is located here, which is in the tangent direction to the curve. Normal direction is acting toward the center. You have done this before, you should be able to obtain the velocity equal to the radius multiplied with the angular velocity. So in the vector format, the velocity is equal to omega crossed with radius. You can obtain the acceleration by differentiate the velocity vector with respect to time. Then you need to differentiate omega with respect to time to obtain the omega dot. Remain the r, plus you differentiate the r with respect to time, and then remain the omega. So this is the result. You need to be careful for a particle that is doing the circular motion. So in this case, the radius will be equal to constant. If you want to know what is the dr over dt in this case, since the r is constant, therefore you obtain 0. This is scalar analysis because we are using the scalar quantity r for the calculation. However, in this study, we can no longer treat the rigid body as the particle here. We are performing the vector analysis for the rigid body instead of the scalar analysis. So don't mix the usage here. You must understand what is the r vector here. In this case, you have the r vector changed with respect to the rotation. So at a particular moment, you have the r vector here. At the next moment, the r vector will be changed in terms of direction. Previously, in the relative motion analysis, you have learned this equation. The change of the unit vector I to the I dot here with respect to time is equal to the angular velocity of the frame multiplied with the unit vector I. In this case, we have the displacement vector r here, which is changing the direction. Therefore, you have the dr with respect to time here, which is equal to the angular velocity due to the rotation for the object, omega, crossed with the r. So you see this term is not equal to 0, but is equal to omega cross r. Substitute inside, then you obtain the acceleration component to be the omega dot cross r plus the omega cross this term, which is the omega cross r. And you found that this term is exactly the same with this, which is the tangential velocity. With that, you should obtain the velocity and the acceleration equation in the vector format. We can further simplify this equation by substituting the v inside to obtain the omega cross v. And then for the tangential acceleration, you must know the omega dot here is referred to the angular acceleration. For the ease to understand the vector and acceleration equation here, you can use the analogy for the equation that you form during the scalar analysis by using the normal tangential coordinate. The tangential velocity in the tangential direction here is equal to r omega in the scalar unit and is equal to omega cross r in the vector unit. The total acceleration is equal to the normal acceleration plus the tangential acceleration. So you have the tangential acceleration here, which is equal to alpha crossed with the r, which is change of the magnitude of the tangential velocity with respect to time. On the other hand, the normal acceleration is here, which is equal to omega cross in the bracket of omega cross r. It means that you need to perform the omega cross r inside, then only you perform the omega cross v here. So when you perform this calculation, you are actually computing the normal acceleration, which is also known as the centripetal acceleration. The magnitude of the normal acceleration is equal to v squared over rho, where the rho is equal to r in this case, and you can convert this equation into r omega squared, where the v is equal to r omega. You need to be careful. The magnitude of the normal acceleration is equal to r omega squared for the 2D rotation case only. For the 3D case, if the omega vector is no longer 90 degrees to the displacement vector, then we cannot obtain this equation. So bear in your mind, this equation r omega squared is only valid for 2D case because the omega will be always 90 degrees to the displacement vector. Later you will see in some cases for the 3D motion, you have the omega not perpendicular to the r vector here. In this case, we cannot use the r omega squared to compute it. You have to use the vector triple product here to compute the normal acceleration. If people asking you this question, why is the linear velocity and acceleration at the center of mass here? From this example, you should know now is equal to 0, which can be proved by substitute the radius here equal to 0, then you obtain the velocity and acceleration equal to 0. So this is the 3D view for your velocity and acceleration. For the velocity, you can obtain it by taking the omega here, cross with the radius here. So by using the right hand rule, if you cross this, you obtain a vector which is perpendicular to these two vectors. Therefore, you obtain the velocity in this direction, and this is your tangential velocity. For the acceleration case here, you have omega cross r to be this direction. So if you take the omega and cross with this vector here, as the result of the cross product, you should obtain the acceleration in this direction. So this is your normal acceleration. Lastly, you have the alpha cross with the radius. So this is the direction for alpha and this is the radius. So when you cross this, you obtain the same direction with the tangential velocity, which is here. So you have the velocity and tangential acceleration here in the tangential direction, and you have the normal acceleration acting toward the center.